Welcome back to week 3 discussion of ionic covalent compounds, transition metal compounds. Now I do want to refresh where we are on the concept map. Okay, this is where we started. Our periodic table was the first place where we started. Then we traversed through periodic table to an atom. We learned about orbitals, okay, and then we learned about electronic configuration, okay. And then from the atom we learned about atomic ionic properties. We also like periodic trends like ionization energy and stuff. And then once we learned that, we also tied it back to writing electronic configuration for ions, okay. And we used the Roman numerals to determine like how sodium would make +1 and nitrogen would make N3-. So that's what we were able to get out of the periodic table into the ionic charge. And then we learned from the ionic charge ionic compounds, okay, like sodium plus and Cl minus, we called it ionic, right? And then we learned nomenclature, how to name ionic and covalent compounds, right? Now we learned all this, okay, and then we learned this, we learned this, right? But what we did not learn is we learned about a compound. Like when I talked to you about covalent compounds, I spoke to you with something like this, right? And then with sodium chloride, you see me writing for ionic pluses and minus, but for covalents nothing. That means it has something to do with the bonding, right? So again, knowing all this, now we're going to go and learn this broad area right here, okay, and how, okay, bonding plays a key role towards a molecule's polarity, that is whether it's polar or non-polar, okay. And we're going to use two popular models. One of them is the VS-EPR model and the other one is Lewis structures, because the VS-EPR model has some deficiencies which will be corrected by the Lewis structures, okay. So let's delete this. Now I mentioned the word polarity, right? Okay, polar means, okay, typically it is soluble in water, okay, soluble in water. If it's non-polar, okay, that means it's not soluble. Water is the universal solvent, okay. So we base all our discussion based off of water, okay. So water is a solvent and anything you add to it is your solute, okay. A solution, okay, is a combination. This is not deviating from the topic, but very much relevant to what we're going to talk about, okay. Solute and solvent, okay. A solute is typically smaller in proportion and solvent is usually larger in proportion. If your compound, okay, is polar like sodium chloride, which is table salt, okay, it is going to be soluble in water because sodium chloride is ion. So how do we know something is polar or non-polar? Okay, that has to do with the bonding, okay. Just because I tell you sodium chloride is ionic, because what did we say? What compounds do make ionic? Well, it has to be a metal and a non-metal, right? If this is the combination, okay, that's a classic example of ionic. There's no problems with it, okay. But it is this covalent compound that we learned has two kinds, okay. One is polar covalent, okay, and then non-polar covalent, which I don't know why they have to have a category called non-polar covalent when non-polar covalent is essentially covalent compounds, okay. But we're going to learn about it because this is soluble in water because it's ionic, is polar compounds, okay. Non-polar covalent is more polar, okay, and non-polar covalent, as you guessed it, is more non-polar, okay. And all this is governed by your electronegativity and bonding, okay. So that's what we're going to learn, okay. So ionic compounds are more polar, they're immediately soluble in water. because like dissolves like. Water is polar. Okay. So, if your solvent is polar, your solute has to be polar. If your solvent is nonpolar, then your solute has to be nonpolar. Let's write that down. Okay. So, if your solute is polar, that means your solvent also has to be polar. So, ionic compounds which are polar, okay, has to dissolve in something that's polar too. So, if your solute is nonpolar, then your solvent must also be nonpolar. Okay. Now, how do we know ionic compounds are polar? Well, that's where we're getting into, is called bonding. And I think I briefly mentioned about bonding when we talked about when we beginning to start week 3 discussion. Okay. But then I don't think we went in great detail. So, that's the key thing. To keep in mind that any bond, okay, any bond is made of only 2 electrons, made up of 2 electrons. Okay. Now, you will see that I think when I mentioned ionic compounds, that I did not write a pure bond. I kind of wrote it like with a little wedges, and then when I discussed covalent, I wrote a solid line. Okay. So, that is what we are going to come back and touch, because that was not the place to discuss it, but I still wanted to give you that information so that you are ready for it when we learn this one. So, right. So, let's, and how does the bonding, okay, I kept telling you bonding has to do with valence electrons, okay, and valence electrons has to do with the Roman numerals, because you cannot always be writing, electronic configuration for all elements every time you want to build a structure. Okay. Bonding is directly related to valence electrons, and valence electrons are directly related to the Roman numerals, right. So, there are 2 types of electrons. Okay. One is bonding electrons, okay. Bonding electrons means electrons that are involved in a bond, and then there are lone pair of electrons. Okay. Lone pair of electrons. These are not involved in bonding. Okay. Involved in bonding. Okay. And lone pair of electrons non-involved in bonding. Okay. All right. So, let us get that out of the way. So, we have 2 types of electrons. One are the bonding electrons that are actually involved in the bonding process, and there are lone pair of electrons that are not involved in the bonding, but actually govern whether a molecule could be polar or nonpolar. Okay. But before that, let us learn something else that is related to what we are going to learn, and that is Linus Pauling's, okay, electronegativity table. Okay. All right. So, now you do not need to memorize this table. Okay. You do not need to memorize this table. I will probably give this to you on a test. So, rest assured. So, that is not something you have to worry about, right. So, there is a range which I want to focus on. So, if your element, okay, we are going to call something called electronegativity, okay, difference. We are going to learn about something called electronegativity difference. Now, keep in mind this concept works for most compounds, but there are exceptions, which is where your VSEPR or your Lewis structures come in. Okay. I am going to abbreviate the electronegativity difference as EN. Okay. So, these are values that you do not have to remember. I will give you these values on a test. Okay. So, based on the electronegativity difference, we can classify compounds as, okay, if En, the electronegativity difference is 0 to 0.5, okay, the compound is type of compound, okay, is non-polar covalent, okay, right. And then if the electronegativity difference is 0.6 to say 1.6, okay, 1.6, it is polar covalent, and if it is 1.7 and above, okay, it is ionic, okay. So even if you forget that on a test that if you're given a metal and a non-metal, it should make an ionic compound, but say you're not sure whether I have an ionic compound or not, because that governs how you name something, right? This table will be attached to your test, so you can always go back and get the electronegativity difference, right? So let's go practice this with a, okay, let's practice this a little bit more. So this is the table. Let's say I give you a compound, say oxygen, O2, something we breathe, right? And don't worry, I'm going to write the bond. Oxygen's got double bonds, okay, and I think I mentioned it too. So we will talk about bonding in the next video, but here all we're trying to prove is whether this compound is ionic, polar covalent or non-polar covalent. And if you go get the value, oxygen's electronegativity is 3.5. That's same for the two oxygens. So to get the electronegativity difference, you subtract one value from the other. In this case, it doesn't matter which value you put since they're the same, so it's 0, right? Since it is between 0 and 0.5, right, it is non-polar covalent, okay. What it really means is the electrons that make up, you see there's an electron here, electron here, electron here, electron here. Oxygen's got double bonds. Don't worry about the bonding part yet. We are not quite there yet, but just focus on the concept here, which is it's got double bonds and each bond's got 2 electrons, right? When a compound is purely non-polar covalent, what it means is the electrons are equally shared. Okay, the electrons are equally shared between the 2 elements, equally shared between the 2 elements. It doesn't matter what those elements are. If the value is between 0 and say 0.5, okay, I'm actually going to make it 0.6, okay, because it's not that much difference, okay. I think I will go back and change, just for now, just think of it as 0 to 0.6 instead of 0.5. Not that it makes a huge difference, but the electrons are equally shared between the 2 elements, okay. So that is non-polar covalent, okay. All right, so let's get rid of this and bring back our table again. Now let's get hydrochloric acid, okay. Now you don't need to, I've not taught you how to name it, so I'll just give you the compound and its name, okay. I don't know if I can really teach you hydrochloric acid naming, okay. It's HCl, okay. Now let's go get the electronegativity value of hydrogen, which is 2.1, and chlorine is 3.0, right? Right. Now the electronegativity differences, you always subtract the smaller value from the larger value, so it is 0.9. Okay, and if you notice, it's about it's 0.6 and about to 1.6, right? So this is polar covalent, right? When a molecule is polar covalent, okay, the electrons are not equally shared. The electrons continue to lean more towards the side with the most electronegative value of the 2 elements. So there's 2 ways people denote that process, okay. In the oxygen case, we said that because the values are same, the electrons are equally shared between the 2 elements, right. even though we technically have a bond between these two and the bond has 2 electrons, the electrons are not equally shared. It's kind of more lean towards, it kind of has a soft corner towards the side with the most electronegative value. Okay, there's 2 ways that you can represent that idea. One is you can use delta, which is a partial symbol, 50-50 or more like a 60-40 or 70-30, but it's partial. Okay, that's what it comes down to. So out of the 2 elements, hydrogen is lesser value and chlorine is more value. So the whichever one is less gets a positive charge, means out of the 2 this is more electropositive and this is more electronegative. This is one way of telling that the electrons are not technically equally shared, it's partially shared, but it's more towards the side with the more electronegative element. Or there's another way which we will use consistently, is we will use a tail and a head arrow. Okay, the tail indicates, okay, in this arrow, this indicates the side with less electronegativity value. Okay, and you guessed it, this side has higher electronegativity value. Okay, I'm not going to scribble it here, higher electronegativity value. Okay, so this was what 2.1 and this was 3.0. So this is more like, this is higher than this one, so the arrow points towards it. Both representations are correct. All right. Okay, now let's go get this table again. Okay, now let's write our sodium chloride. Okay, we already know sodium chloride is ionic. Okay, and you notice I am not quite writing a bond because there is no bond. It's more of a virtual bond between sodium and chlorine, because the chlorine technically holds both electrons to itself. In the polar covalent, it's like I said, it's more of a 60-40 split. It's not equally shared. But in an ionic, it's more like 100-0. Okay, so you probably also guessed it, how the charges would look like. For sodium, it's 0.9 and chlorine is 3.0, right? So if you take the electronegativity difference, you subtract the smaller value from the larger value, so it's 2.1, which is in the 1.7 to 1.7 and above range, right? So it's clearly ionic, right? When a compound is ionic, the bond that that contains the 2 electrons is really non-existent. It's kind of a virtual bond, if you would think, an imaginary bond. So when a compound is purely ionic, the sodium gets a full positive charge because it has the smallest of the 2 values, and chlorine gets a full negative charge because it's larger of the 2. Okay, so you don't need to even, we don't do neither of those, the tail head, or we don't do this or this, because this is only used when a compound's electronegativity is partial, like it's not a 0 to 100, it's somewhere in between 50-50 to 0 to 100. That's when we use this. So this is exclusively reserved for polar covalence. This is exclusively reserved for ionic. Okay, they get a full positive and a full negative charge. Okay, so I have seen some textbooks do mention this. So this is sodium, this is chlorine. You will see that they put it like this. Okay, that means the bond is really non-existent, but there is a bond, but it's just non-existent. What this really means is both those electrons in the bond are almost towards the chlorine and it's not towards the sodium at all. Right? So that's the difference between the 3. You have the non-polar covalent, which are essentially your covalent compounds. Okay, there's not much difference. It's just another name for covalent. But the reason they had the classification is you do have the pure covalent, and then which is non-polar covalent, and then you have the polar covalent compounds, which are a little bit more polar. They are soluble in water. Yeah, obviously, your sulfuric acid, your hydrochloric acid, they're all soluble in water. So they're polar covalent, and then you have your ionic compounds which are also polar. They're purely polar, then your polar covalent and non-polar covalent / covalent. Okay. So here's what we have learned. We learned polar compounds, if it's purely polar, it has to be ionic. Okay. And then you have polar covalent, okay, which are partially polar, okay, but it's good enough to dissolve in water. Okay. Not all polar covalent compounds are soluble in partially polar, but good enough to be soluble in water. So ionic compounds are completely soluble in water. If you take your sodium chloride, dissolve it in water, it is soluble in water. Partially polar, they're also soluble in water to a certain extent. And then you have your non-polar covalent, aka just covalent. Okay, I'm going to write it. So you think it's, don't think of it as some kind of separate category, but because they are classifying it as polar covalent, they just had to write it as non-polar covalent. They're the same, they are completely non-polar. Okay, means they are insoluble in water. Okay, chemistry is full of exceptions, so you know we're not going to go too far into the exceptions. All right, so this is how we classify a compound as ionic, polar covalent, or non-polar covalent. Now again, you do not have to remember that electronegativity table. It will be stapled to your test, or if you're taking your quiz or homework, I guess you can always use it to solve any problems pertaining to it. In the next video, we're actually going to go more detail into the bonding. Remember I said the bonding is related to the valence electrons, and the valence electrons are related to the Roman numerals, right? So that's what we're going to get into next, and we're going to talk about the various types of geometry that can make and how that geometry affects a molecule's polarity. All right, okay, very good. So let's continue our discussion on bonding in the next video. Okay, stay tuned.